Alright, so there's our basic forms. Let's rewind a little bit, come back to tan, and sometimes they give you a slightly different question. They'll say tan x is equal to tan something else, okay? Alright? Or sometimes they'll say, tan 3x is equal to tan 5x. What do you do? Okay? Well, I'm going to follow this pattern again, but I'm going to notice that C, right? Or tan inverse of C, if what I've got for C is also itself tan something, right? I'm going to have tan inverse of tan this angle, right? Tan inverse of tan, which for the domain that we're interested in, it's just they're just going to cancel, right? So you've got to remember tan inverse of tan x is equal to x only within certain domains, right? Because if you take x out to some other, like some crazy large angle, like say 15 pi or something like that, you get tan of that, and then when you take tan inverse, it goes back within your normal domain. Okay, so this is only sometimes, but it's good enough for us because we always want those sometimes, right? So therefore, if I've got this situation, then I can change it a little bit. Instead of saying x equals tan inverse of c, I can just put that as alpha. That will be the angle I'm interested in. Okay, plus n pi, and the same thing applies. Okay, same logic here. If cos x is equal to cos alpha, right, this kind of format, therefore x is equal to 2n pi plus or minus your base angle, which will just be alpha. And one more time, if, excuse me, sine x equals sine alpha, again I'm going to replace this thing on the end with n pi plus the switching thing, alpha. Okay, now, so what I've got in black is the basic forms. What I've got in blue, I kept on forgetting this, but anyway, you get the idea. You do have to say that, because you can't just introduce variables at random. Okay. What I've got in blue is where you've got trig functions on both sides. And then you noticed as well that, for instance, with this one and with this one, even though we like having everything in terms of one equation, because that's nice and neat, and it captures everything anyway, when you've got alpha, like if this was 3x and 5x, we noticed that we could do some simplifying here, right? We could say if this was 3x and this was 5x, I could take the 5x over and I could I could collect like terms, right? That was the useful thing. But to do that, you've got to break the equations apart again in order to actually make that happen, okay? So, let's consider, I'm going to rub off these graphs. Let's consider what happens to these general solutions when we break them back into two. Because I remember, I'm spending some more time on this because I remember how many people got confused by this. Why were we, I thought it was good to have things in one. Why did we break them apart again? What's the point? Okay. So, example. Let's do the one that I've just been talking about. Okay. So in this case, we just start off at this point here. Right? Except instead of x and alpha, I've got 3x and 5x. Okay. Usually the tradition is to keep the bigger number as your subject. It doesn't really matter, your numbers will come out the same. You just have less negatives flying around. You'll see why in a second. So I'm going to make that my first angle. Okay, that's equal to 2n pi plus or minus 3x. So far so good, just straight substitution. Okay. Now this is correct. Like it's fine, but I can make it simpler by breaking it back apart. So let's do that. Okay. Over here on the left-hand side, I can say, let's take the case where it's negative. Okay, so it's 2n pi minus 3x. Okay, so because I can take this over now, I can work with it now that I just have one here. Add 3x to both sides, so you get 8x. And of course, we just want 1x on its own. So that will be n pi on 4. Okay, then you take the other side, and you say, well, let's treat the positive case. 2n pi plus 3x. Again, you get a like terms, so 2x. By the way, you can see if I put 3x over here and 5x over there, it would still work. I'd just get a double negative, and I'd have to cancel that out. Okay. 2x divided by 2, so ta-da. And then you notice, hold on a second, all of these solutions, because this is shorthand for 0 pi, 1 pi, 2 pi, 3 pi, and so on. All of these solutions are already included in this set. right? Because this is 0 pi on 4, 1 pi on 4, 2 pi on 4, etc. Okay? So 4 pi on 4 corresponds to 1 pi, right? So therefore, you know, even though this is true, I actually don't need to worry about it. This is fully sufficient. Okay? Does anyone ask me any questions on that? Now that's cosine. Sine's a bit trickier because of this this switching thing in here. So I'm going to get rid of tan and cos, and let's have a think about cosine. Sine, sorry. Okay, so let's do 3x and 5x again. Okay, sine 3x. Sorry, I want to do black. Sine 3x and sine 5x. Okay, so I start by writing just the one equation. Okay, so I'm going to get 5x is equal to n pi plus your switching thing times 3x. Okay, and just as before, like we had with the plus or minus, I can't simplify this any further in its present form because that switching thing, I can't do anything to simplify it, right? So, how do I break this apart into its two forms? Okay, well you remember, what we're trying to take into account here is that for odd values of pi, it does one thing, and for even values of pi, it does another thing. Okay, so I want to think about the odd and even bits. Let's think about the even ones first, okay, because that's 0, starts from 0, and then 2 pi, and then 4 pi, and so on. So if I want even lots of pi, and from even ones I'm going forward, aren't I, for sine, okay? All the even numbers are, this is 5x, all the even numbers are 2 and pi, aren't they? 2n pi. That'll give me 0, 2, 4, 6, 8. Okay? So this is looking a little bit like the cosine one, right? For the even lots, I go forward. So plus 3x. Okay? I did it blue. Anyway. So, there we go. Blue. Okay? It's important for me. Alright, now I can simplify, take the 3x across. 2x equals 2n pi. So x equals, that looks familiar, doesn't it? Okay. Should look familiar because it's just like the cosine one. Exactly the same result. Then when you do this part, odd values of pi, how do we get odd values? What's a way, what kind of expression can we use to generate all the odd numbers? Well, there's two different ways, right? I can go 2n minus 1, or I can go 2n plus 1. Can you see they give me exactly the same set of numbers? Because I'm thinking of all of the n's, all of the integers, okay? The reason why I'm making a note of that, I'll go with minus, is because two legitimate different ways, right? I could make it a plus or a minus, and I'd get different answers at the end. So this is the explanation for why you go to your textbook, you've solved the general solution, and you're like, mine is totally different to theirs. Well, maybe it's not that different. It just looks different, okay? I'll just leave it. Okay, so this is the odd values of pi, and for the odd values, you have to go backwards, okay, of your base 8. So now I simplify. 8x equals 2n plus 1 pi. So x is, how should I write this? 2n plus 1 pi on 8. Okay? Now, unlike with our cosine example, okay, this guy here and this one here, they do not overlap, right? In fact, they never overlap, do they? 2n plus 1. Yeah, they should never overlap, because I'm always going to have odd numbers here over an even denominator, so it will never simplify out to be just the whole number. Okay? So in this case, I've got to include both. So my final conclusion is x equals n pi, or pi on 8 to n plus 1 for those values. Okay? So, I remember people getting very, very confused by particularly the sine one, because you start out with this cool switching thing, and then it just vanishes, and starts to look like cosine. My brain, what's going on? Okay? All we're doing is, we're breaking it apart for the purpose of simplifying further. See, these lines are working. We cannot do so long as that minus 1 to the n is there. Okay? So, there's your general solutions.